Problem set number 4, question number 8, for real this time. I'm doing a one-tailed hypothesis test, and in particular I'm interested in the right tail. This means that the result that will get me published, the result that will make the news, is if the population mean is greater than, pointing to the right, greater than 211. And conversely, my null hypothesis is the opposite of that. It would be less than or equal to 211. So the direction I care about is greater than. Similar to before, I'm going to identify a rejection region. Now my rejection region, I've highlighted here in yellow, needs to match the direction of the results that I care about. So again, I get published if my results are greater than 211, off to the right. So my rejection region is also going to be greater than 211. Similar to before, I want to identify a threshold, and we'll assign a number to that called the critical value. And the critical value is the point that differentiates my rejection region from my do not reject region. And the area of that rejection region is going to be the significance level. So remember from before, we have a confidence level. We want to be confident in our results. So this is usually some number that's 90% or above. And we have 1 minus the confidence level. We have the complement, and that is equal to the significance level. So this is going to be a smaller number, like 0.1 or 0.05. In this question, the significance level is 0.1. It's the same thing as alpha. Because I'm doing a one-tailed test, all of that significance goes into, imagine this, one tail. So for a two-tailed test, I had a one rejection region over here and another rejection region over here. And I had to take that significance level, that 10%, and divide it into two. And I had 5% over here and 5% over here, so that I could have a significant result be if my mean was less than or greater than 211. In this case, I don't care about the less than. I only care about a greater than 211. So I only have one rejection region, and all of that significance level probability, that whole 10%, goes into that one side. So the area under the curve, the size of my rejection region, the probability of rejecting my result will be 0.1. With that, we go ahead and do the same kind of thing that we did before. We need to calculate the actual value for the critical value. That critical value, again, is the number of standard errors away from the mean that will give me a probability of 0.1. We have an Excel function for that. It starts with a t because, like before, this is a t distribution. The dot inverse tells us that we're going to give Excel a probability, which will be based on the significance level, and we want a distance out of it in standard error units. We want to know how far away the critical value is from the mean in standard error units, given that we need to create this much area, an area of 0.1. The syntax, the structure of the .excel function, is t.inv, and then you have to give it, just because this is the way Excel works, you have to give it the complement of the significance level. So we want to end up with 0.1%. Excel does everything starting from minus infinity and moving off to the right. So we need to give it this area, and it'll calculate where that kind of upper cutoff is. So we give it to the complement of the significance level, which we know happens to be the confidence level. So we give it the confidence level, we give it the degrees of freedom, number of data minus 1, and Excel will happily tell us that the critical value, the number of standard errors away from the mean, is 1.89. So after we move 1.89 standard errors from the mean, we are left with 10% of our area. Like before, just having the critical value itself doesn't do us a whole lot of good. We have to compare that to our actual data. Our data in this case is X bar, a sample mean of 167. Now that 167 is in original data units. Our critical value is in standard error units, so that doesn't do us a whole lot of good. We need to convert that 167 into standard error units so we can compare it to the critical value. So we do that. I haven't used green yet, so we'll go here. We do that by calculating the t-score, just as we did before. And the t-score, even though we went from a two-tailed test to a one-tailed test, our t-score formula hasn't changed. It's still the sample mean, 167, minus the population mean, 211. And then we take that distance in original data units and convert it to standard error units. So we divide by the standard error. And that tells us that our data, just like before, our sample mean, is minus 5.5 standard errors away from the mean. So that minus means we're going to move to the left of the mean. So we are 5.5 standard errors to the left of the mean. This is just where we were before with our two-tailed test. So even though we changed the number of tails, we have not changed kind of the location of our sample mean. So now we have a critical value, we have a t-score. These are the two things that we can compare, and that gives us one of our ways of dealing with hypothesis tests. It allows us to to reject or fail to reject the null hypothesis. Now, even though we have a large number, 5.5 is big, it is, or at least big in terms of magnitude, it is not more extreme than the critical value. Our critical value is up here at positive 1.8. Now 5.5 is big, but we haven't crossed our threshold. We haven't crossed 1.89 because, yeah, and even though it's big, we're moving off to the left. We're moving in a direction that we don't care about. We only care about big values, and our value is big in terms of standard errors, but in the wrong direction. So because our t-score, because our data, our sample mean, is not more extreme than the critical value, we've not crossed this threshold that we actually care about, we have not ended up in our rejection region, then we do not reject our null hypothesis. We fail to reject the null hypothesis. And that gives us our first answer. And I will just end it here and then do the p-value and confidence interval next.